Breaking news from the edge of our solar system. We are witnessing something unprecedented, something that is fundamentally rewriting the rules of astronomy as we speak. The object known as 3I Atlas is no longer behaving like a simple comet. In fact, researchers are quietly admitting they might be looking at something they have no framework to understand. Days ago, astronomers watched as this interstellar visitor crossed within 2 astronomical units of the Sun and began brightening far beyond any prediction. Its atmosphere has swollen to half the diameter of our star. Its glow has shifted to an unsettling, almost alien green, and, most bizarrely, it's developed a tail pointing directly toward the Sun, a feat that should be impossible as it races toward Mars at breakneck speed. The countdown to its closest approach to the Sun, its perihelion, has begun, and with every passing hour, this alien wanderer looks less like a comet and more like a cosmic riddle, demanding answers. Stay with us as we unravel what this breaking story means for everything we thought we knew, and explore what happens when alien chemistry, dormant for billions of years, finally awakens under our Sun's relentless glare. In mid-September 2025, astronomers monitoring 3I Atlas noticed something unsettling in their data streams. The brightness measurements, which had been following a predictable curve, began to climb. They weren't just inching up, they were surging, rising from an expected magnitude of 15 or 16 to a startling 12 to 14. For those who don't speak the backward language of astronomy, let me explain. Magnitude numbers run in reverse. The lower the number, the brighter the object. A drop of just 2 magnitudes means the object is now producing 6 times more light than predicted. But this wasn't a gradual change. This was an acceleration. The Comet Observation Database, known as COBS to those who track these celestial wanderers, began showing data points that climbed steadily above the standard upward slope expected for a warming comet. Observations from telescopes across Earth confirmed the trend. 3I Atlas was outshining every single model astronomers had constructed for its journey sunward. The critical moment came as the object moved inside approximately 2 astronomical units of the Sun in early to mid-September. For context, $1 is the distance from Earth to our star, roughly 93 million miles. At $2, 3I Atlas was still twice as far from the Sun as we are, yet something fundamental changed. The brightness acceleration wasn't just unexpected. It was alarming in its intensity. So, what could cause such a dramatic surge in luminosity? The textbook explanation involves volatile ices, frozen carbon dioxide, water, and exotic compounds locked within the nucleus since the object's formation around another star. As solar radiation intensifies, these materials don't just melt. They explosively transition from solid to gas, carrying dust and debris in expanding clouds that reflect sunlight back toward Earth. But here's what should concern us. Rapid brightening events often signal instability. Comets experiencing sudden outgassing can fragment, creating multiple objects or spectacular debris clouds. They can also exhaust their volatile reserves quickly, leading to equally rapid dimming. The fact that 3I Atlas is brightening faster than models predict suggests we're witnessing processes that astronomers don't fully understand. Now, before anyone panics, let's be perfectly clear. This is not a cause for planetary alarm. NASA has confirmed that 3I Atlas maintains a safe distance, never approaching closer than 1.8 astronomical units to Earth, nearly twice the distance to our Sun. The alarm isn't about collision. It's about comprehension. We may be watching an interstellar time capsule undergo fundamental changes in real time as it barrels toward the inner solar system. Consider the implications. This object formed in the disk of debris around another star, perhaps hundreds of light years away. It condensed from materials that never felt our Sun's warmth, never experienced the specific conditions that shaped the bodies native to our cosmic neighborhood. Yet now, for the first time in its existence, it's encountering the intense radiation environment of our inner solar system. This brightness surge could represent the awakening of chemistry that has remained dormant for millions or billions of years. Exotic ices, stable in the frigid depths of interstellar space, might now be sublimating for the first time since the object's birth. We are potentially witnessing the unveiling of chemical signatures from another star system, preserved in pristine condition across the galaxy. The timing creates additional urgency. 3I Atlas is approaching a series of critical dates that will determine what astronomers can learn from this unprecedented visitor. October 3rd marks its closest approach to Mars, a mere 18.6 million miles. That's close enough for spacecraft orbiting the red planet to potentially observe details invisible from Earth. Then, by late October, specifically October 29th to 30th, the comet reaches perihelion, its closest approach to the Sun, at approximately 1.36 astronomical units. And here's where the story takes a deeply troubling turn. As 3I Atlas nears its date with our star, its position in our sky moves dangerously close to the Sun's overwhelming glare. From early October through early November, the comet enters what astronomers call superior conjunction, a period when the Sun's brightness makes observation nearly impossible from Earth's surface. This means the peak activity of our interstellar visitor, the moment when solar heating reaches its maximum intensity and the comet's true nature might be revealed, will occur largely hidden from our view. We will be forced to rely on the mechanical eyes of spacecraft positioned throughout the solar system, particularly those orbiting Mars, to witness what could be the most spectacular display of interstellar chemistry in human history. The brightening trends suggest 3I Atlas won't go quietly through perihelion. Current observations hint at an object energized by its encounter with our Sun, possibly building toward outburst events that could illuminate previously invisible details of its structure and composition. But will these revelations occur during the weeks when Earth's telescopes are blinded by solar glare? To understand why 3I Atlas is so special, we need to go back to the beginning of its story. It all started on a mountaintop in Chile, where robotic eyes scan the night sky with a mechanical precision that puts human observers to shame. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected a faint smudge of light moving against the background stars. Initially catalogued as just another minor body, this unremarkable observation would soon rewrite our understanding of interstellar visitors. What makes an object interstellar isn't simply its origin beyond our solar system. It's the mathematical certainty that it can never be gravitationally bound to our Sun. 3I Atlas follows what astronomers call a hyperbolic trajectory, a path so energetic that once it completes its swing around our star, it will continue outward forever, never to return. The orbital mathematics are unforgiving in their precision. This object carries too much velocity to be captured by our Sun's gravity. The 3I designation tells its own story. The I stands for interstellar, while the number 3 indicates this is only the third such object confirmed in human history. Its predecessors, 1I Oumuamua in 2017 and 2I Borisov in 2019, each surprised astronomers with unique characteristics that defied easy categorization. Now, 3I Atlas continues this pattern of interstellar unpredictability. The discovery process reveals just how difficult these objects are to catch. Atlas operates from the Rio Hurtado Valley in Chile's Atacama Desert, part of a global network designed to spot potentially hazardous asteroids approaching Earth. The system captures multiple images of the same sky region over short time periods, then uses computer algorithms to identify anything that moves against the stellar background. On that July night, 3I Atlas appeared as little more than a faint streak, barely distinguishable from the thousands of asteroids, comets, and space debris that populate our inner solar system. But recovery images, earlier photographs that show the object before its official discovery, revealed that 3I Atlas had been lurking in astronomical databases for weeks before anyone recognized its significance. This delayed recognition is common with interstellar objects, which often appear asteroidal in early observations before developing the fuzzy comas and tails that mark them as comet-like bodies. The initial assessment showed a faint coma surrounding the central nucleus, immediately suggesting that 3I Atlas was more than just a rocky asteroid. Comets develop these fuzzy atmospheres when solar heating causes ices to sublimate, creating expanding shells of gas and dust. The presence of a coma so far from the Sun, 3I Atlas was still beyond 3 astronomical units when discovered, indicated that this object contained volatile materials capable of outgassing even in the cold outer reaches of our solar system. As news of the discovery spread through the astronomical community, larger telescopes began turning toward this new interstellar visitor. The Hubble Space Telescope captured detailed images in July, while the Very Large Telescope in Chile and other ground-based observatories contributed their data. These follow-up studies revealed an object far more complex than its initial discovery images had suggested. Size estimates for 3I Atlas remain frustratingly uncertain, a common problem when studying objects too distant and faint for direct measurement. Hubble's August update narrowed the possibilities to a nucleus somewhere between 0.2 and 3.5 miles in diameter, a range that reflects the difficulty of separating the solid nucleus from its surrounding coma. This size uncertainty matters because it affects calculations of the object's mass, density, and structural stability as it approaches the Sun's intense heating. Speed calculations, however, paint a clearer picture of this object's extraordinary nature. Currently racing through space at approximately 130,000 miles per hour, 3I Atlas moves at velocities that dwarf anything naturally occurring in our solar system. For comparison, Earth orbits the Sun at a sedate 67,000 miles per hour. The comet's speed will continue increasing as solar gravity accelerates it toward perihelion, potentially reaching 152,000 miles per hour. These velocities underscore the alien nature of our visitor. No object born in our solar system could naturally achieve such speeds without assistance from gravitational slingshot maneuvers around massive planets. 3I Atlas carries the kinetic signature of its interstellar origin, accumulated during millions of years of travel through the galaxy under the influence of stellar gravitational fields and galactic rotation. The rarity of confirmed interstellar visitors makes each one precious to science. Before 2017, astronomers had only theoretical models to guide their understanding of how objects might behave during interstellar journeys. 1I Oumuamua shattered many assumptions with its elongated shape and mysterious non-gravitational acceleration. 2I Borisov appeared more conventionally comet-like but revealed chemical compositions unlike anything in our solar system. Now, 3I Atlas adds a third data point to this sparse collection, and early indications suggest it will prove as unique as its predecessors. The object's behavior challenges models in new ways, particularly its unexpectedly large coma and unusual brightness evolution. Each interstellar visitor seems to carry its own set of physical and chemical rules, suggesting that the galaxy harbors far more diversity in small body formation processes than we previously imagined. The classification process involves more than just confirming interstellar status. Astronomers must also determine whether 3I Atlas represents an asteroid-like body, a comet, or something entirely different. The presence of a coma strongly suggests comet-like behavior, but the specific gases and dust compositions revealed through spectroscopic analysis ultimately determine how this object formed and evolved in its birth star system. This is not a local comet kicked inward from the Oort cloud, that distant reservoir of icy bodies. 3I Atlas formed around another star, condensed from materials that experience different temperatures, pressures, and chemical environments than anything native to our cosmic neighborhood. It represents a direct sample of planetary formation processes that occurred light years away, possibly billions of years ago. The trajectory calculations place 3I Atlas on a path that will provide unprecedented observation opportunities, particularly during its close approach to Mars on October 3rd. This geometry isn't accidental. the object's orbital inclination and timing aligned favorably for spacecraft observations, just when Earth-based telescopes will lose sight of it due to solar glare. But understanding what we're seeing requires more than just knowing where 3I Atlas came from and where it's going. The real mysteries lie in how it's behaving as it encounters our sun's radiation for the first time in its existence, and why that behavior differs so dramatically from theoretical predictions. Time is running out for 3I Atlas, and for the astronomers racing to understand it before it vanishes into the solar glare. The cold, unyielding mathematics of orbital mechanics have drawn a precise roadmap through the inner solar system, marking critical dates that will determine what humanity can learn from our third confirmed interstellar visitor. October 3rd, 2025, represents the first crucial milestone. On this date, 3I Atlas will sweep past Mars at a distance of approximately 18.6 million miles. In cosmic terms, this is an extremely close encounter, placing the interstellar visitor well within the operational range of the multiple spacecraft currently orbiting the red planet. The timing is both fortuitous and deeply frustrating. Just as 3I Atlas reaches its closest approach to Mars, offering these spacecraft the clearest possible view of an interstellar object in action, Earth-based telescopes begin losing their ability to track it. The cruel geometry of orbital mechanics places the comet increasingly close to the Sun's position in our sky, creating observational challenges that will soon become insurmountable. Then, in late October, specifically October 29th to 30th, 3I Atlas reaches perihelion, its closest approach to the Sun, at approximately 1.36 astronomical units. This distance places it just inside Mars's average orbital radius, subjecting the interstellar visitor to solar radiation intensities unlike anything it experienced during its multi-million-year journey through the galaxy. The timing coincides almost perfectly with the period of greatest observational difficulty from Earth. The speed of this object tells its own dramatic story. Currently traveling at over 130,000 miles per hour, 3I Atlas will reach its maximum velocity near perihelion, potentially hitting 152,000 miles per hour. To put this in perspective, Earth maintains its stable orbit at roughly 67,000 miles per hour. 3I Atlas will be moving more than twice as fast as our entire planet. These velocities are more than just impressive statistics. They reveal the fundamental physics governing interstellar motion. Unlike objects native to our solar system, which have spent billions of years settling into their orbits, 3I Atlas carries the kinetic energy of its journey between stars, a souvenir from its gravitational slingshot around its unknown parent star. The real challenge lies in the observational geometry. From early October through early November, 3I Atlas experiences what astronomers call superior conjunction, a period when its position in Earth's sky places it too close to the Sun for practical observation. The solar elongation, the angular separation between the comet and Sun as seen from Earth, drops below 30 degrees, and then below 20 degrees. Imagine trying to spot a firefly hovering right next to a powerful searchlight, and you begin to understand the predicament. Even the most sophisticated telescopes on Earth cannot separate the faint light of 3I Atlas from the overwhelming glare of our star when the two appear close together in the sky. This creates a fundamental irony in the 3I Atlas encounter. Just as solar heating reaches its maximum intensity and the comet potentially undergoes its most dramatic transformations, Earth's astronomical community will be effectively blinded. The peak outgassing, possible fragmentation events, and maximum tail development could all occur during the weeks when our most powerful ground-based telescopes are useless. This observational gap places extraordinary importance on the spacecraft positioned around the solar system, particularly those orbiting Mars. The European Space Agency's Mars Express and Trace Gas Orbiter, along with NASA's Mars Reconnaissance Orbiter and MAVEN, suddenly find themselves in the role of humanity's primary eyes on one of the most significant astronomical events of the decade. The handoff from human telescopes to robotic ones will be one of the most critical moments in this entire encounter. The most immediately astonishing discovery about 3I Atlas isn't just its interstellar origin or its unusual trajectory. It's the sheer, impossible scale of the atmosphere it's creating around itself. In September 2025, NASA's Spitzer Space Telescope detected something that defied every model astronomers had constructed for comet behavior: an extended carbon dioxide coma stretching an incredible 216,000 miles from the nucleus. To grasp the magnitude of this, consider this ghostly atmosphere extends roughly half the diameter of our Sun. The coma of 3I Atlas has grown large enough to contain Mercury's entire orbit. This isn't just unusual, it's unprecedented in the annals of cometary science. A coma forms when solar radiation heats the ices locked within a comet's nucleus, causing them to sublimate directly from solid to gas. Think of it as a cosmic snowball steaming in sunlight, but that analogy fails to capture the violence of the process. As frozen materials explosively transition to gas, they carry dust particles and larger debris outward, creating an expanding atmosphere that, in this case, has grown to proportions we've never seen. The composition of 3I Atlas's coma tells a story of formation under conditions radically different from our solar system. The dominance of carbon dioxide over water vapor suggests this object condensed in a region where CO2 could freeze out more readily than H2O, possibly in the outer, frigid reaches of another star's planetary disk, where temperatures remained low enough for carbon dioxide ice to remain stable while water existed primarily as vapor. This CO2-rich environment is a direct hint at the chemical conditions present during 3I Atlas's birth. Most comets in our solar system show water as their primary volatile component. The reversed ratio observed here indicates formation temperatures and pressures unlike anything experienced by objects native to our cosmic neighborhood. But the coma's composition isn't its only unusual characteristic. Images from the Hubble Space Telescope and ground-based observatories reveal a structure that challenges fundamental assumptions about comet behavior. Instead of the classic tail streaming away from the Sun, 3I Atlas displays what astronomers call an anti-tail, a plume of material that appears to point sunward. This sunward-pointing structure represents a puzzle that has kept researchers working through sleepless nights. Conventional comet physics is simple. Solar radiation pressure should push gas and dust away from the Sun, creating the familiar tails that have inspired human imagination for millennia. Yet 3I Atlas seems to be violating this basic principle. Hubble's July 21st observations captured what mission scientists described as a forward glow. Follow-up imaging by the Gemini South Telescope showed this unusual geometry persisting and evolving, suggesting the anti-tail is a stable feature, not a temporary fluke. The physics behind anti-tail formation are complex. They can involve large dust grains, too massive to be easily pushed by solar photons, that maintain their original trajectories if ejected with sufficient velocity. It can also be a trick of perspective, a projection effect that makes material moving in a curved orbit appear to point toward the Sun from Earth's vantage point. However, theoretical models struggle to explain the persistence and prominence of 3I Atlas's sunward plume. It appears too well-defined and long-lasting to result from a simple illusion. Recent analysis suggests the anti-tail might result from unusual rotation states or surface properties unique to interstellar objects. A slowly spinning, irregularly shaped nucleus could develop extreme temperature differences, concentrating outgassing into powerful directional jets. Alternatively, the surface composition of 3I Atlas might include materials that respond to solar heating in ways completely unfamiliar to researchers accustomed to studying local comets. The coma's expansion rate adds another layer to the mystery. Spectroscopic observations indicate that gas velocities within the coma exceed typical values for comets at similar distances from the Sun. This enhanced outgassing could result from the release of supervolatile compounds that remain stable only in interstellar conditions, sublimating with explosive force when first exposed to significant solar heating. As 3I Atlas continues its approach toward perihelion, the coma continues growing and evolving, potentially reaching even more mind-boggling dimensions. Modeling efforts to predict its future evolution face unprecedented challenges. The unusual composition, anti-tail geometry, and enhanced outgassing rates all require modifications to standard cometary physics models. Researchers are effectively developing new theoretical frameworks in real time. The implications extend far beyond 3I Atlas itself. If interstellar comets routinely display such bizarre Coma characteristics, it suggests that our understanding of comet physics, based primarily on objects from our own solar system, may represent only a narrow subset of what's possible in our galaxy. In the middle of September 2025, 3I Atlas did something that sent ripples of excitement and unease through the astronomical community. It turned green, not gradually, not subtly, but with a vivid, emerald glow that transformed this interstellar visitor from a pale, fuzzy smudge into something that looked almost alive against the star-filled darkness. The color change wasn't immediately obvious to the naked eye. 3I Atlas remains too faint for that. But sensitive cameras attached to telescopes around the world began capturing images that showed an unmistakable green tint surrounding the comet's nucleus. The transformation became particularly evident in photographs taken during the lunar eclipse on September 14th, when the moon's shadow provided darker skies that heightened the contrast of the comet's newfound luminescence. This green glow tells a story written in the language of quantum mechanics. When certain molecules absorb ultraviolet light from the sun, their electrons jump to higher energy states. As these excited electrons fall back to their normal state, they emit light at specific wavelengths that our eyes perceive as distinct colors. In the case of 3I Atlas, the green emission most likely originates from diatomic carbon, two carbon atoms bonded together, designated as C2. Diatomic carbon behaves like a molecular neon sign in space. When energized by solar ultraviolet radiation, C2 molecules emit light at a wavelength around 516 nanometers, producing that characteristic green glow. This emission process, called resonance fluorescence, transforms invisible solar energy into visible light that can travel across millions of kilometers to reach our telescopes. But here's where the story becomes deeply puzzling. Early spectroscopic observations of 3I Atlas showed relatively little evidence for carbon-bearing compounds. The initial chemical analysis suggested a composition dominated by carbon dioxide and water vapor, with only trace amounts of the carbon-rich molecules typically responsible for green comet colors. This is a glaring contradiction. We're seeing a strong green glow, but we can't find the chemical that should be causing it. Researchers are scrambling to understand this discrepancy. One compelling possibility involves phase transitions in the comet's outgassing behavior. As 3I Atlas moved closer to the Sun and crossed the $2 threshold in early September, increased solar heating may have begun sublimating previously inaccessible deposits of carbon-rich materials buried deep within the nucleus. These materials, locked away during its long interstellar journey, might now be experiencing solar radiation for the first time in billions of years. The timing is suspiciously perfect. The green color change correlates almost exactly with the period of rapid brightening observed in mid-September. This suggests that the same physical processes responsible for the unexpected brightness surge, possibly the catastrophic release of volatile materials from subsurface reservoirs, also triggered the chemical reactions producing the green emission. The evolution of the green glow provides additional clues. Unlike the steady emission expected from simple molecular fluorescence, observations suggest the green color varies in intensity and distribution within the coma. Some regions appear more intensely green than others, suggesting that carbon-bearing molecules aren't uniformly distributed. This could result from discrete jets of material erupting from specific locations on the nucleus, each with a slightly different chemical composition. The appearance of green coloration in 3I Atlas adds another data point to the growing catalog of differences between interstellar visitors and native solar system objects. 1I Oumuamua showed no cometary activity and thus no color changes. 2I Borisov displayed more conventional comet colors. 3I Atlas represents the first interstellar comet to develop the classic green coma, yet the specific intensity and timing may reveal chemical compositions unique to its birth star system. The green glow transformation represents more than just a visually striking development. It provides direct evidence that 3I Atlas is undergoing fundamental chemical changes as it encounters our sun's radiation. The molecules now fluorescing in the comet's coma have likely remained chemically inert for eons, preserved in frozen silence during the object's journey between stars. Now, for the first time since its formation, 3I Atlas is literally lighting up as solar energy activates chemical processes that have been dormant since the comet's birth around another star. That green glow marks the awakening of alien chemistry. Behind the measured language of scientific papers and the carefully qualified statements in astronomical bulletins, something approaching excitement and, yes, alarm, is rippling through the global community of comet researchers. 3I Atlas isn't behaving according to the script written by decades of cometary science, and astronomers are beginning to admit, in the cautious way that scientists acknowledge uncertainty, that they might be witnessing something unprecedented. The brightness trend documented by observers worldwide represents more than statistical noise or measurement error. Multiple independent tracking systems, from the Comet Observation Database to specialized amateur networks, show the same unsettling pattern. 3I Atlas consistently outshining the predictions derived from standard cometary models. The magnitude of this deviation, several brightness levels above expected values, falls well outside the margins typically attributed to observational uncertainty. Dr. Matthew Knight, a cometary scientist at the University of Maryland who has spent his career studying how these objects behave, recently noted in an interview that the rapid brightening event observed in mid-September challenges fundamental assumptions about volatile release mechanisms in comets. The speed of the change indicates processes operating on timescales much faster than the gradual heating models typically used to predict comet behavior. This scientific uncertainty breeds a particular type of excitement among researchers, the recognition that they might be observing phenomena that will require new theoretical frameworks to understand. The sunward-pointing plume structure generates its own category of scientific puzzlement. Anti-tail phenomena aren't completely unknown in cometary science, but the persistence and prominence of 3I Atlas's forward-directed jets push the boundaries of what existing models can easily explain. Researchers find themselves proposing increasingly exotic scenarios: unusual dust grain compositions, non-uniform nucleus rotation, exotic volatile mixtures, to account for behavior that defies textbook explanations. What everyone in the field agrees on is that 3I Atlas is demonstrating enhanced activity levels compared to typical comets at similar distances from the Sun. The carbon dioxide-dominated coma detected by Spitzer, extending to unprecedented distances, suggests outgassing rates that exceed standard predictions by significant margins. This isn't a subtle deviation from theory, it's a dramatic departure that demands explanation. Yet the scientific community also grapples with what researchers call outburst bias, the tendency for comets to undergo brief periods of enhanced activity that can create false impressions of sustained, unusual behavior. Comets are notoriously prone to sudden brightness surges followed by equally rapid returns to predicted levels. The question haunting 3I Atlas observations is whether the September brightening represents a genuine departure from normal behavior or simply a temporary outburst that will fade as quickly as it appeared. This uncertainty becomes more troubling when considered against the backdrop of the approaching observational gap. Dr. Carey Holt, who studies interstellar objects at the European Southern Observatory, expressed the frustration felt by many researchers. The exact moment when 3I Atlas might reveal its most significant secrets coincides with the period when Earth-based astronomy becomes least capable of observing it. The timing represents what I'd term a cosmic conspiracy against scientific understanding. The debates extend beyond simple brightness measurements to fundamental questions about what 3I Atlas represents as a physical object. Its chemical composition, revealed through spectroscopic analysis, shows ratios of carbon dioxide to water vapor unlike those typical of solar system comets. This difference could indicate formation conditions radically different from our local environment, or it might reflect chemical processing that occurred during millions of years of interstellar travel. Social media within the astronomical community reflects a mixture of scientific excitement and professional caution. Researchers share preliminary images and brightness measurements while carefully noting the uncertainties and limitations in their data. The tone suggests scientists are aware they're observing something potentially significant, while remaining professionally skeptical about drawing premature conclusions. Conference presentations scheduled for the American Astronomical Society's Division for Planetary Sciences meeting include multiple talks focused on 3I Atlas observations and theoretical modeling efforts. The abstracts reveal research groups worldwide attempting to understand not just what 3I Atlas is doing, but why existing models fail to predict its behavior accurately. The sense of urgency among researchers reflects more than scientific curiosity. It represents the recognition that opportunities to study interstellar objects remain extraordinarily rare, with only 3 confirmed interstellar visitors in human history. Each object provides irreplaceable data about conditions in other star systems and the processes that govern small body formation throughout the galaxy. International collaboration has intensified as the observational window narrows. Telescopes in Chile, Hawaii, the Canary Islands, and Australia coordinate observations to maximize coverage as 3I Atlas approaches the solar conjunction period that will end routine Earth-based monitoring. Each facility contributes unique capabilities, from high-resolution imaging to specialized spectroscopic instruments, in an effort to extract maximum scientific value from the remaining observation opportunities. While Earth prepares to lose sight of 3I Atlas in the solar glare, another world positions itself for a front-row seat to one of the most significant astronomical events in recent memory. On October 3, 2025, Mars will host humanity's closest encounter with an interstellar visitor, offering spacecraft orbiting the red planet unprecedented opportunities to observe 3I Atlas from a vantage point Earth-based telescopes can only dream of achieving. The geometry couldn't be more fortuitous. As 3I Atlas sweeps past Mars at a distance of approximately 18.6 million miles, multiple spacecraft currently operational in Martian orbit will have the opportunity to turn their instruments toward this cosmic visitor. The timing places these observations just days before superior conjunction makes Earth-based tracking impossible, creating a crucial handoff from terrestrial to space-based monitoring. The European Space Agency's Mars Express orbiter, launched in 2003 and still functioning far beyond its original mission timeline, carries the high-resolution stereo camera that has mapped Martian terrain in unprecedented detail for over 2 decades. While designed for planetary geology, HRSC possesses the sensitivity and resolution potentially needed to capture detailed images of 3I Atlas's nucleus and coma structure. Dr. Colin Wilson, project scientist for the ExoMars Trace Gas Orbiter, confirmed that mission planners are evaluating opportunities for both the color and stereo surface imaging system, CASIS, and the nadir and occultation for Mars Discovery Nomad spectrometer to observe the interstellar visitor. These instruments, designed to study Martian atmospheric composition and surface features, might be capable of detecting chemical signatures within 3I Atlas's expanding coma. NASA's Mars Reconnaissance Orbiter presents perhaps the most intriguing possibilities for detailed observations. The high-resolution imaging science experiment, HiRISE, routinely captures surface details smaller than a meter across from its orbital altitude. While 3I Atlas will pass much farther away, HiRISE's extraordinary resolution might resolve structural details of the comet's nucleus that remain invisible to Earth-based telescopes. The MAVEN spacecraft, Mars Atmosphere and Volatile Evolution Mission, carries spectrographic instruments specifically designed to analyze atmospheric composition and dynamics. These capabilities could prove valuable for studying the chemical composition of 3I Atlas's coma, particularly the carbon dioxide-rich gases that dominate its spectroscopic signature. However, the observational opportunities come with significant technical challenges. All Mars orbiters were designed and optimized for studying the red planet itself, not for tracking fast-moving objects against the stellar background. The spacecraft's pointing systems, developed for observing a large, nearby planet, must be reconfigured to follow a small, distant target moving at interstellar velocities. Signal strength represents the most fundamental limitation. Even at its closest approach to Mars, 3I Atlas will appear extremely faint to spacecraft instruments designed for planetary rather than deep space observations. The comet's magnitude, estimated around 12 to 14 even during its brightening phase, pushes the detection limits of most Mars orbiter cameras and spectrometers. Dr. Wilson acknowledged these limitations in recent communications with the international astronomical community, noting that while Mars-based observations of 3I Atlas are theoretically possible, the actual scientific return depends on factors including the comet's brightness at closest approach, atmospheric conditions on Mars, and the specific geometric arrangements required for successful pointing. The advantage of Mars-based observations extends beyond simple proximity. The viewing geometry from Mars during the October 3rd flyby provides a perspective on 3I Atlas unavailable from Earth. Solar phase angles, the angle between the Sun, comet, and observer, will differ significantly between Mars and Earth viewpoints, potentially revealing details of Coma structure and tail geometry hidden from terrestrial telescopes. Solar-wind interactions present another area where Mars orbiters might contribute unique observations. 3I Atlas's encounter with the solar wind, the stream of charged particles flowing outward from the Sun, could produce phenomena detectable by the plasma and magnetic field instruments carried by several Mars missions. These interactions might reveal information about the comet's internal structure and composition through changes in its magnetic and electrical properties. The European Space Agency's coordination efforts for the Mars flyby observations involve unprecedented cooperation between missions designed for entirely different scientific objectives. Mars Express, originally planned for surface geology and atmospheric studies, finds itself repurposed as an interstellar object observatory. The Trace Gas Orbiter, focused on methane detection and atmospheric chemistry, must adapt its instruments for cometary spectroscopy. Timing constraints add complexity to observation planning. Mars orbiters follow predetermined schedules for routine planetary observations, communication windows with Earth, and spacecraft maintenance activities. Inserting 3I Atlas observations into these schedules requires careful coordination to avoid conflicts with primary mission objectives while maximizing scientific opportunities. The data transmission challenges are substantial. Mars orbiters typically communicate with Earth during specific windows when both planets' orbits provide favorable geometry for radio transmission. Images and spectra of 3I Atlas must compete with routine planetary science data for limited communication bandwidth, potentially delaying the release of observations by weeks or months. The scientific value of successful Mars-based observations could prove transformative for understanding 3I Atlas. High-resolution imaging might resolve the nucleus size and shape with unprecedented precision, settling debates about the comet's physical dimensions and structure. Spectroscopic observations could detect molecular species invisible from Earth-based telescopes, revealing chemical compositions that preserve information about the comet's formation environment. Structural details of the coma and tail, particularly the unusual sunward-pointing plume that has puzzled researchers, might become clearer when viewed from Mars's unique perspective. The different solar phase angle could reveal whether the anti-tail structure results from genuine sunward ejection of material or represents a projection effect that appears different from various viewing angles. Yet reality requires managing expectations about what Mars orbiters can achieve. Even under optimal conditions, the scientific return from these observations will likely consist of a handful of images and spectra rather than comprehensive monitoring campaigns. The instruments were never designed for this type of observation, and their capabilities may prove insufficient to answer the fundamental questions about 3I Atlas's nature and behavior. Success depends on variables beyond human control. If 3I Atlas undergoes another brightening event before October 3rd, it might become detectable to Mars orbiter instruments that would otherwise find it too faint to observe. Conversely, if the comet fades from its current enhanced brightness levels, even the most optimistic observation scenarios might yield no useful data. The Mars flyby represents humanity's best opportunity to maintain surveillance of 3I Atlas during the critical weeks when Earth-based telescopes lose sight of this interstellar visitor. As terrestrial astronomy prepares for an imposed silence lasting through early November, the mechanical eyes orbiting Mars offer the only hope of witnessing what may prove to be the most dramatic phase of 3I Atlas's encounter with our solar system. Whether these observations succeed or fail, they mark a new chapter in how humanity studies visitors from other star systems, demonstrating our growing capability to coordinate observations across multiple worlds, even as the objects of our attention race past at interstellar velocities. The mathematics of celestial mechanics are utterly indifferent to human curiosity. As October progresses and 3I Atlas continues its relentless approach toward the Sun, the geometric realities of orbital motion conspire to snatch away our interstellar visitor precisely when it might reveal its most profound secrets. Superior conjunction, that period when 3I Atlas appears too close to the Sun's position in our sky for practical observation, transforms one of the most significant astronomical events in recent memory into a cosmic vanishing act. The timeline unfolds with merciless precision. In early October, 3I Atlas drops below 30 degrees of solar elongation, the threshold where serious observational difficulties begin for ground-based telescopes. Atmospheric scattering of sunlight creates a brightening sky background that overwhelms the faint signal from our interstellar visitor. By mid-October, elongation decreases to less than 20 degrees, effectively ending routine observations from Earth's surface. The comet doesn't disappear suddenly. It fades gradually into the solar glare, like a star at sunrise, becoming increasingly difficult to detect until observation becomes impossible. The conjunction period extends through early November, encompassing roughly 4 to 5 weeks when 3I Atlas remains effectively invisible from Earth. This isn't simply an inconvenient gap in observations. It represents the complete loss of our ability to monitor the comet during what theoretical models predict should be its most active period. The cruel irony becomes more apparent when considered against the backdrop of 3I Atlas's recent behavior. The rapid brightening observed in September, the unusual anti-tail structure, and the distinctive green coloration all suggest an object undergoing fundamental changes as it encounters our sun's radiation. Logic dictates that these transformations should intensify as solar heating increases, potentially reaching spectacular levels near perihelion in late October. Yet perihelion occurs almost exactly at the midpoint of the conjunction period, when 3I Atlas appears closest to the Sun in Earth's sky, and observation becomes most impossible. The timing couldn't be worse for understanding what this interstellar visitor truly becomes when subjected to maximum solar influence. The physics behind superior conjunction involve no conspiracy against scientific discovery, merely the geometric consequences of observing from a planet orbiting the same star as our target. As 3I Atlas approaches perihelion, its apparent position in the sky necessarily approaches the Sun's location. Solar observing satellites like the Solar and Heliospheric Observatory, SOHO, can sometimes track comets during conjunction periods using coronagraphs that block the Sun's direct light. However, 3I Atlas's trajectory doesn't pass close enough to the Sun for detection by these specialized instruments, which typically observe objects within a few solar radii of our star. The conjunction gap creates unprecedented challenges for a scientific community accustomed to continuous monitoring capabilities. Modern astronomy relies heavily on long-term observation campaigns that track objects through complete cycles of activity. Comets, in particular, require extended monitoring to distinguish between temporary outburst events and sustained changes in behavior. Spacecraft positioned throughout the solar system offer limited alternatives to ground-based observations, but their capabilities remain constrained by original mission designs focused on planetary rather than cometary studies. The Mars orbiters provide the most promising near-term opportunities, but their observations will be brief snapshots rather than the continuous monitoring needed to fully understand 3I Atlas's evolution. The European Space Agency's BepiColombo mission, currently en route to Mercury, follows a trajectory that might provide occasional opportunities to observe 3I Atlas from a different vantage point. However, the spacecraft's instruments are optimized for Mercury studies, and the geometric requirements for comet observations may not align favorably with mission operational constraints. NASA's Parker Solar Probe, designed to study the Sun's corona and solar wind, operates in the inner solar system where it might theoretically encounter 3I Atlas's tail or Coma material. However, the probe's highly elliptical orbit and focus on solar rather than cometary phenomena limit its utility for systematic comet observations. When Earth-based observations resume in November or early December, 3I Atlas will likely have changed dramatically from the object astronomers studied in September. The comet may have brightened further, possibly developing spectacular tail structures. Alternatively, it might have faded significantly if volatile materials became depleted during the unobserved perihelion passage. More dramatically, 3I Atlas might have fragmented into multiple pieces during its closest approach to the Sun-comet. Fragmentation isn't uncommon near perihelion, where tidal forces and thermal stresses can overcome the weak gravitational binding holding nucleus materials together. If fragmentation occurs during conjunction, Earth-based observers will face the challenging task of identifying and tracking multiple objects when observations become possible again. The resumption of observations in late November or December will require careful planning and coordination among observatories worldwide. 3I Atlas will emerge from conjunction in a different region of the sky, requiring telescopes to locate and reacquire the comet. After weeks of invisibility, the object's brightness, position, and appearance may have changed sufficiently to complicate identification and tracking efforts. Public interest in 3I Atlas faces its own conjunction-related challenges. Media coverage of astronomical events typically relies on dramatic images and continuous updates to maintain audience engagement. The forced silence during the conjunction period eliminates the steady stream of new observations that sustain public attention, potentially reducing interest just as the comet experiences its most significant transformations. Educational opportunities also suffer during the conjunction gap. Schools and amateur astronomy groups often use bright comets as tools for teaching about solar system dynamics and observational techniques. 3I Atlas's most photogenic period, when tail development and nuclear activity could provide the most visually spectacular educational content, will occur largely unseen. The conjunction period serves as a humbling reminder of astronomy's fundamental limitations. Despite centuries of technological advancement, humans remain bound to their home planet for most astronomical observations, subject to the geometric constraints imposed by Earth's position relative to observed objects and the Sun. As 3I Atlas vanishes into solar glare, the astronomical community prepares for a period of speculation and theoretical modeling based on incomplete data. The question isn't whether the comet will change during its hidden passage. It's whether those changes will be comprehensible when observations resume, or whether the conjunction gap will leave permanent mysteries about what happened during the most critical phase of this interstellar visitor's encounter with our Sun. Deep within the solar glare that blinds Earth's telescopes, 3I Atlas prepares for its appointment with destiny. On October 29th to 30th, 2025, this interstellar wanderer will reach perihelion, its closest approach to the Sun, at approximately 1.36 astronomical units. Hidden from human observation, the comet will experience solar radiation intensities unlike anything in its multimillion-year journey between star systems, potentially undergoing transformations that could redefine our understanding of interstellar objects. The speed evolution alone tells a story of cosmic violence. Currently racing through space at over 130,000 miles per hour, 3I Atlas will reach its maximum velocity near perihelion potentially hitting 152,000 miles per hour. To appreciate this extraordinary speed, consider that Earth maintains its stable orbit at roughly 67,000 miles per hour. 3I Atlas will be moving more than twice as fast as our entire planet, carrying kinetic energy accumulated during its epic journey across the galaxy. Physics predicts that perihelion will trigger the most dramatic phase of 3I Atlas's solar system encounter. As solar heating reaches maximum intensity, the temperature of the comet's nucleus will soar, potentially activating volatile compounds that have remained stable throughout its interstellar voyage. Water ice, carbon dioxide, carbon monoxide, and more exotic frozen gases could all begin sublimating simultaneously, creating an explosive expansion of the Coma that might dwarf the already unprecedented dimensions observed in September. The increased outgassing could produce spectacular dust jets erupting from discrete locations on the nuclear surface. These jets, formed when subsurface volatile deposits find pathways to escape, can create fountain-like structures extending thousands of kilometers into space. The sunward-pointing anti-tail that has puzzled observers might intensify dramatically, or entirely new tail structures could emerge as different volatile compounds begin contributing to the Coma for the first time. Theoretical models suggest that 3I Atlas's carbon dioxide-rich composition might produce perihelion behavior unlike that of typical solar system comets. Carbon dioxide sublimes more readily than water ice at the temperatures expected near perihelion, potentially creating gas production rates that exceed those of water-dominated comets by significant factors. This enhanced activity could manifest as rapid changes in brightness, coma size, and tail structure occurring over periods of hours rather than the days or weeks typically associated with comet evolution. The possibility of fragmentation looms over perihelion predictions like a shadow of uncertainty. Comets represent some of the most fragile objects in the solar system, held together by weak gravitational forces and the structural integrity of their icy matrices. The thermal stresses induced by intense solar heating, combined with the mechanical forces generated by explosive outgassing, can overcome these binding forces and tear nuclei apart. Fragmentation events can unfold with dramatic suddenness. A comet that appears stable during its approach to perihelion can split into multiple pieces within hours as thermal gradients create structural weaknesses or gas pressure eruptions excavate material from the nucleus interior. The historical precedent for comet fragmentation near perihelion includes spectacular examples like Comet Shoemaker-Levy 9, which broke apart under Jupiter's tidal forces before impacting the planet in 1994. More recently, Comet Ison disintegrated during its extremely close approach to the Sun in 2013, creating a debris cloud that dispersed rapidly as it moved away from perihelion. However, fragmentation isn't inevitable. The structural integrity of 3I Atlas depends on factors including nucleus composition, internal porosity, rotation rate, and the specific thermal stresses generated by its unique volatile mixture. Interstellar objects might possess structural characteristics that differ significantly from solar system comets, potentially making them more or less susceptible to thermal disruption. The speed at which 3I Atlas passes through perihelion also influences fragmentation risk. Unlike some comets that linger near their closest solar approach, 3I Atlas will sweep past perihelion relatively quickly due to its hyperbolic trajectory. This rapid passage limits the duration of peak heating, potentially reducing the cumulative thermal stress experienced by the nucleus. If 3I Atlas survives perihelion intact, the post-perihelion period should reveal an object transformed by its encounter with intense solar radiation. The Coma might expand to even larger dimensions as peak gas production rates distribute material across unprecedented volumes of space. New chemical species liberated from subsurface deposits by deep heating could appear in spectroscopic observations for the first time. Color changes beyond the green emission already observed might develop as different molecular species begin fluorescing under solar ultraviolet radiation. Complex organic compounds, if present in the nucleus, could break down into simpler fragments that emit light at characteristic wavelengths, potentially creating a rainbow of emissions across the visible spectrum. The anti-tail phenomenon that has characterized 3I Atlas observations might evolve dramatically near perihelion. Enhanced dust production could create multiple tail structures pointing in different directions as particles of various sizes respond differently to solar radiation pressure. The resulting geometry could provide crucial information about the nucleus rotation rate, surface composition, and internal structure. Dust grain analysis becomes particularly important during the perihelion period. The size, distribution, and composition of particles ejected from the nucleus reflect the internal structure and formation conditions of the original object. Large grains might indicate a loosely consolidated nucleus with significant void spaces, while fine dust could suggest a more compact structure or specific chemical compositions that favor the production of small particles. The magnetic and plasma environment near perihelion adds another layer of complexity to 3I Atlas's behavior. The solar wind, charged particles streaming outward from the sun, interacts with the ionized gases in the comet's Coma to create complex electromagnetic phenomena. These interactions can accelerate particles to high velocities, create visible glows in the Coma, and influence the development of plasma tails that extend millions of kilometers behind the nucleus. The aftermath of perihelion will depend critically on how much volatile material 3I Atlas contains and how efficiently that material can escape through the nuclear surface. Objects with large volatile reserves might continue showing enhanced activity for weeks or months after perihelion, while those with limited volatile content could fade rapidly as their surface layers become depleted. The perihelion passage represents the climax of 3I Atlas's solar system encounter, the moment when billions of years of interstellar evolution meet the intense radiation environment surrounding our star. Whether this meeting produces spectacular displays of cosmic pyrotechnics or quiet structural transformations hidden within an expanding Coma, perihelion will fundamentally alter 3I Atlas from the object that entered our solar system into something new and unprecedented. The question that will haunt astronomers through the conjunction period is whether 3I Atlas will emerge from its hidden perihelion passage recognizable as the same object that captivated observers in September, or as something entirely transformed by its encounter with our sun's most intense radiation. The answer lies hidden in solar glare, awaiting the patient geometry of orbital mechanics to reveal what perihelion has wrought. The scientific community's response to 3I Atlas resembles a detective story where crucial evidence remains locked away, forcing researchers to construct theories from incomplete clues. While the most important information lies hidden behind solar glare, multiple competing hypotheses attempt to explain the comet's unusual behavior, each raising new questions that may remain unanswered until post-conjunction observations provide the missing pieces of this interstellar puzzle. Hubble Space Telescope observations have narrowed the size estimate to somewhere between 0.2 and 3.5 miles in diameter. But this broad range reflects the fundamental challenge of separating the solid nucleus from its extensive Coma. This uncertainty matters profoundly because size directly affects calculations of mass, density, surface area available for outgassing, and structural stability during intense heating. Different measurement techniques produce conflicting results. Thermal modeling based on infrared observations suggests a smaller nucleus with high albedo, a reflective surface that efficiently scatters sunlight. Visible light analysis indicates a larger, darker nucleus that absorbs more solar radiation. This discrepancy could result from surface composition variations, measurement uncertainties, or fundamental misunderstandings about how 3I Atlas responds to solar heating. James Webb Space Telescope spectroscopy clearly identifies carbon dioxide as the dominant volatile species in 3I Atlas's Coma, with CO2 concentrations exceeding those of water vapor by significant margins. This composition differs dramatically from solar system comets, where water typically dominates volatile inventories. However, the carbon dioxide dominance creates theoretical problems for explaining other observed characteristics. The green coloration that developed in September typically indicates diatomic carbon emission, but CO2-rich outgassing doesn't naturally produce the carbon-bearing molecules responsible for green fluorescence. Either the spectroscopic analysis missed important chemical constituents, or the green coloration results from processes more complex than simple molecular fluorescence. Ground-based spectroscopic observations from the Very Large Telescope and other major observatories have detected additional molecular species, including cyanide compounds and various organic molecules. These detections hint at chemical complexity beyond the simple CO2 dominance indicated by space-based observations, suggesting that 3I Atlas contains a diverse inventory of both simple and complex carbon-bearing compounds. The anti-tail structure presents perhaps the most perplexing observational puzzle. Conventional comet physics dictates that solar radiation pressure should push gas and dust away from the sun, creating tails that point radially outward from the solar direction. 3I Atlas appears to violate this fundamental principle by ejecting material that forms structures pointing toward the sun rather than away from it. Dr. Zhang and Dr. Loeb's recent theoretical analysis, currently undergoing peer review, proposes that the anti-tail results from unusual dust grain size distributions combined with specific ejection geometries from the nucleus surface. Their model suggests that large dust particles ejected sunward with sufficient initial velocity can overcome solar radiation pressure to create the observed forward-pointing structures. However, competing models invoke different physical mechanisms. Some researchers propose that electromagnetic effects, interactions between charged dust particles and solar magnetic fields, could redirect material in unexpected directions. Others suggest that 3I Atlas's rotation state creates temperature asymmetries that concentrate outgassing in specific directions regardless of solar radiation pressure. The rotation period of 3I Atlas remains unknown despite months of observation attempts. Light curve analysis, which measures brightness variations caused by an irregularly shaped nucleus rotating in sunlight, has failed to reveal clear periodic signals. This absence of detectable rotation signatures could indicate either very slow rotation, a nearly spherical shape, or rotational complexity that obscures simple periodic variations. Rotation state affects multiple aspects of comet behavior. Rapidly spinning objects experience centrifugal forces that can influence outgassing patterns and structural stability. Slowly rotating comets develop temperature differences between day and night sides that concentrate volatile release in heated regions. The unknown rotation characteristics of 3I Atlas complicate efforts to model its thermal evolution and predict future behavior. The brightness evolution documented in September presents its own interpretive challenges. Multiple observation networks confirmed that 3I Atlas became significantly brighter than theoretical predictions, but the magnitude of this deviation remains debated. Some observers report brightness increases equivalent to several magnitude levels, while others suggest more modest enhancements that fall within the normal range of comet variability. The discrepancies arise partly from measurement difficulties. 3I Atlas remains near the detection limits of most telescopes, making accurate photometry challenging even under optimal conditions. Different observers use different comparison stars, filter systems, and reduction procedures that can introduce systematic errors into brightness measurements. More fundamentally, the lack of baseline observations complicates brightness trend analysis. Unlike periodic comets that have been observed through multiple apparitions, 3I Atlas represents a single opportunity target with no historical data for comparison. Researchers must rely on theoretical models based on solar system comets to establish expected behavior, but these models may not apply to objects formed in other star systems. Origin studies attempt to trace 3I Atlas's trajectory backward through the galaxy to identify its probable birth location. Current kinematic analysis suggests the comet originated somewhere within the Milky Way's thin disk, the flat star-forming region where most current stellar activity occurs. However, the uncertainties in measured position and velocity propagate backward through time, creating increasingly large error ellipses that encompass multiple possible source regions. The galactic origin question has implications for understanding 3I Atlas's composition and age. Objects ejected from young star systems might retain different chemical signatures than those originating from older, more evolved stellar environments. The carbon dioxide dominance could reflect formation in a protoplanetary disk with temperature and chemical gradients unlike those that produced solar system objects. The extensive coma and anti-tail structure suggest vigorous outgassing that could indicate either a volatile-rich nucleus or one undergoing structural disruption. Some researchers propose that 3I Atlas represents a loosely bound collection of smaller objects, a rubble pile held together by weak gravitational forces that could fragment under thermal or tidal stresses. Alternative models treat 3I Atlas as a monolithic object with unusual surface properties or internal structure that produces the observed outgassing patterns. The distinction matters for predicting behavior near perihelion, where thermal stresses and tidal forces reach maximum intensity. The observational gap during conjunction creates additional uncertainty about which theoretical models best explain 3I Atlas's behavior. The most critical tests of competing hypotheses, how the comet responds to maximum solar heating, whether fragmentation occurs, how outgassing patterns evolve, will occur largely hidden from Earth-based observation. When 3I Atlas emerges from conjunction in late November, researchers will face the challenge of interpreting observations of an object that may have changed dramatically during its invisible perihelion passage. The post-conjunction appearance could either validate current theoretical models or introduce new puzzles that require entirely different explanations. The scientific debates surrounding 3I Atlas reflect the broader challenge of understanding phenomena that occur only rarely and under conditions that push observational capabilities to their limits. Each measurement carries uncertainty, each model makes assumptions, and each interpretation must account for the possibility that interstellar objects operate according to physical principles not yet discovered through solar system experience. Before venturing into the realm of truly speculative possibilities, science demands that we exhaust the exotic but still plausible natural explanations for 3I Atlas's bewildering behavior. The comet may be strange beyond current understanding, but it likely remains within the boundaries of known physics, albeit operating under conditions so extreme that they've never been observed before in human experience. The carbon dioxide dominance detected in 3I Atlas's Coma provides the first clue to understanding its alien nature through conventional cometary science. This composition suggests formation in a region of its birth star system where temperatures remained low enough for CO2 to condense into solid ice while water existed primarily as vapor. Such conditions typically occur beyond what astronomers call the carbon dioxide snow line, the distance from a star where carbon dioxide can freeze out of the gaseous phase. In our solar system, the CO2 snow line lies much farther from the Sun than the regions where most comets form. This explains why solar system comets show water as their primary volatile component, with carbon dioxide playing only a secondary role. However, other star systems could have different temperature profiles, stellar luminosities, or chemical compositions that place the CO2 snow line at distances where significant comet formation occurs. A star cooler than our Sun would push the carbon dioxide snow line closer in, allowing CO2-rich comets to form in the same orbital regions where water-dominated objects condense in our system. Alternatively, a star with different chemical composition, perhaps enriched in carbon relative to oxygen, could produce protoplanetary disks where carbon dioxide formation is favored over water ice formation regardless of temperature. The formation environment hypothesis explains not only 3I Atlas's unusual chemistry but also its enhanced outgassing behavior. Carbon dioxide sublimes more readily than water ice at the same temperature, potentially producing gas release rates that exceed those of water-dominated comets by significant factors. This enhanced volatility could account for the rapid brightening observed in September and the unprecedented size of the coma. However, the CO2-rich composition alone cannot explain the sunward-pointing anti-tail that has puzzled observers since the first detailed images appeared. This is where dusty plasma physics enters the equation, introducing processes that operate at the intersection of solid mechanics, gas dynamics, and electromagnetic phenomena. When solar ultraviolet radiation ionizes gases in a comet's coma, it creates a plasma, a soup of electrically charged particles that respond to both gravitational forces and electromagnetic fields. This ionized material interacts with charged dust grains in complex ways that can produce self-organizing structures unlike anything predicted by simple gravitational and radiation pressure models. Charged dust particles can form streams, filaments, and even spiral structures when influenced by magnetic fields carried in the solar wind. Under specific conditions, these electromagnetic effects might overcome radiation pressure, allowing material to flow in directions that appear to violate basic comet physics. The result could be anti-tail structures that point toward the sun while conventional tails stream away from it. The plasma physics explanation gains credibility when considering 3I Atlas's enhanced outgassing rates. Higher gas densities create more opportunities for ionization and charge exchange processes that could amplify electromagnetic effects. The unusual chemical composition might also influence plasma formation through molecular species that ionize more readily or at different rates than those typical of solar system comets. Rotation state offers another avenue for explaining 3I Atlas's anomalous behavior through conventional physics applied to extreme conditions. A nucleus with very slow rotation could develop temperature differences between its day and night sides that concentrate outgassing in specific regions rather than distributing it uniformly across the surface. If 3I Atlas rotates slowly enough that its dayside reaches significantly higher temperatures than solar system comets experience, thermal expansion and gas pressure could create jets of material ejected with velocities high enough to overcome solar radiation pressure in the sunward direction. The result would be preferential ejection toward the sun from the hottest regions of the nucleus surface. The slow rotation hypothesis requires explaining why 3I Atlas would rotate differently from typical comets. Interstellar objects experience different evolutionary processes during their journeys between star systems. Collisions with interstellar dust particles, gravitational torques from passing stars, or magnetic field interactions could all alter rotation states in ways that don't occur for objects remaining within single stellar systems. Surface composition variations offer another natural explanation. Rather than a uniform nucleus composition, the object might contain discrete regions with different chemical makeups, some rich in carbon dioxide, others containing water ice, and still others harboring complex organic materials. As 3I Atlas approaches the sun and different regions of its surface experience heating for the first time, these chemical variations could produce outgassing patterns that change over time. Porosity and internal structure also influence comet behavior in ways that could explain 3I Atlas's anomalous characteristics. A highly porous nucleus, essentially a loose collection of ice and dust held together by weak forces, could allow deep penetration of solar heating that activates subsurface volatile deposits normally insulated from external temperature changes. The enhanced porosity hypothesis explains both the extensive coma and the rapid brightness changes. Deeper heating activates larger volumes of volatile material than typically occurs in more compact comet nuclei, creating gas production rates that exceed model predictions based on surface heating alone. Interstellar processing during 3I Atlas's journey between star systems might have created structural modifications not experienced by solar system objects. Cosmic ray bombardment, interstellar dust impacts, or thermal cycling during passages through different radiation environments could all alter nucleus properties in ways that influence behavior when the object finally encounters intense stellar radiation. The most likely explanation for 3I Atlas's extraordinary behavior involves combinations of these natural processes operating simultaneously. CO2-rich composition drives enhanced outgassing. Plasma physics creates anti-tail structures. Slow rotation concentrates activity in specific regions, and complex chemistry produces the observed color changes. While each individual process remains within well-understood physics, Their interaction under the extreme conditions of an interstellar comet encounter might produce phenomena that appear impossible when considered through the lens of solar system comet experience. 3I Atlas could represent a profoundly weird comet rather than something fundamentally alien, but that weirdness makes it precisely the type of object that could revolutionize our understanding of small body physics throughout the galaxy. Now we venture into territory where science fiction meets speculative possibility, where the boundaries between natural phenomena and truly extraordinary explanations begin to blur. While no credible evidence supports these exotic interpretations of 3I Atlas's behavior, the comet's unprecedented characteristics invite the kind of speculation that has accompanied every unexplained astronomical phenomenon throughout human history. These ideas exist not as serious scientific hypotheses, but as thought experiments that illuminate just how strange our interstellar visitor truly is. The alien technology beacon hypothesis represents perhaps the most persistent exotic explanation for unusual astronomical objects. Ever since Oumuamua's discovery sparked debates about artificial origins, each new interstellar visitor inevitably generates speculation about possible technological signatures. The beacon scenario imagines 3I Atlas as a dormant technological artifact that remained inactive during its long journey between star systems, preserving power and structural integrity until encountering conditions that trigger preset activation protocols. The brightening event in September could mark the moment when solar radiation reached sufficient intensity to power dormant systems, while the anti-tail structure might represent directed energy emissions or material ejections serving some technological purpose. However, this technological interpretation faces immediate challenges when confronted with observational evidence. The spectroscopic signatures detected by James Webb Space Telescope and ground-based observatories show clear evidence for standard volatile compounds, carbon dioxide, water vapor, and organic molecules that match expectations for natural comet outgassing. No unusual isotopic ratios, artificial materials, or energy signatures characteristic of advanced technology have been detected. The quasi-living plasma hypothesis ventures even further into speculative territory, drawing on research into complex plasma behaviors that can exhibit seemingly organized patterns under specific conditions. Laboratory experiments have demonstrated that dusty plasmas, mixtures of charged particles and microscopic solid grains, can self-organize into structures that exhibit properties reminiscent of biological systems. Some researchers have speculated that such complex plasma systems might arise naturally in space environments, potentially developing behaviors that mimic primitive life forms. 3I Atlas's unusual outgassing patterns, anti-tail structures, and responsive brightening could theoretically represent manifestations of such plasma-based phenomena. The living plasma concept suggests that interstellar space might harbor forms of organization that operate according to physical principles completely different from carbon-based biology. These hypothetical entities might remain dormant during interstellar travel, but become active when encountering the electromagnetic environments surrounding stars, producing observable effects that mimic but don't truly represent biological processes. Yet this explanation requires invoking physical mechanisms that remain purely theoretical. While dusty plasmas can indeed form complex structures under laboratory conditions, scaling these phenomena to comet-sized objects operating in the solar wind environment requires extrapolations far beyond current scientific understanding. The purposeful scout narrative transforms 3I Atlas into an active reconnaissance mission from another star system, complete with programmed behaviors designed to study our solar system during its passage through the inner regions. This scenario imagines the comet's unusual characteristics as intentional features rather than natural phenomena. The extensive Coma might provide sensor capability or communication range, while the anti-tail structure could represent data transmission systems aimed at distant receivers. The Scout hypothesis suggests that 3I Atlas's brightening represents not random outgassing but controlled activation of observation and communication systems as the object approaches its primary mission targets. This interpretation leads to romantic speculation about 3I Atlas waking up as it encounters the radiation signature of our star system, its artificial consciousness stirring after millions of years of dormant interstellar travel. The green coloration might mark the moment when dormant sensors begin functioning, while the rapid brightness changes could indicate data processing and transmission activities. However, the Scout scenario faces the same evidentiary challenges as the technological beacon hypothesis. The chemical signatures, thermal behavior, and structural characteristics of 3I Atlas all match expectations for natural objects, albeit unusual ones. No evidence suggests information processing, directed communications, or other activities characteristic of technological systems. The exotic matter hypothesis proposes that 3I Atlas contains materials or operates according to physical principles unknown to current science. Theoretical physics suggests possibilities for exotic forms of matter with unusual properties, dark matter interactions, modified gravitational behaviors, or quantum effects operating on macroscopic scales that could produce observable phenomena unlike anything in standard physics. Exotic matter could potentially explain 3I Atlas's unusual anti-tail through gravitational anomalies that redirect material flow, or account for its enhanced outgassing through energy release mechanisms beyond conventional chemistry. The rapid brightening might reflect exotic phase transitions or energy storage systems that operate according to physics yet to be discovered. This explanation allows for natural phenomena that nonetheless transcend current scientific understanding, suggesting that 3I Atlas represents not artificial technology but natural processes involving physics that human science hasn't yet encountered. The object could serve as an inadvertent laboratory for studying physical principles that don't manifest under conditions typical of Earth-based research. The temporal anomaly speculation ventures into the most exotic territory, suggesting that 3I Atlas might represent some form of information or matter transfer across cosmic timescales. Science fiction scenarios imagine the comet as a message or artifact from our own future, sent backward through time using technologies that circumvent conventional causality constraints. This interpretation treats 3I Atlas's unusual properties as evidence for temporal manipulation rather than spatial travel between star systems. The object might originate from a future version of our own solar system, carrying information or materials intended for our current epoch. Its strange behavior could reflect interactions between future technology and present-day physical conditions. However, temporal manipulation scenarios require physics that not only remains unproven but contradicts fundamental principles of causality and thermodynamics as currently understood. No observational evidence suggests that 3I Atlas violates conservation laws or exhibits temporal anomalies beyond the normal relativistic effects expected for high-velocity objects. The critical perspective on all these exotic explanations emphasizes how often apparently mysterious astronomical phenomena receive mundane explanations once sufficient data becomes available. Pulsar discoveries initially generated speculation about artificial signals from advanced civilizations, but these objects proved to be rapidly rotating neutron stars. Fast radio bursts sparked similar debates before being traced to natural astrophysical processes. History suggests that 3I Atlas will ultimately find explanation within known physics, albeit perhaps involving processes or conditions not previously observed. The comet's unusual characteristics likely reflect the extreme diversity of conditions present in other star systems, rather than manifestations of exotic physics or artificial technology. The value of exploring these speculative scenarios lies not in their probability, but in their ability to highlight just how extraordinary 3I Atlas truly is within the context of human astronomical experience. An object that can seriously inspire considerations of alien technology, living plasma, and exotic matter represents something genuinely unprecedented in our understanding of interstellar visitors. As 3I Atlas continues its hidden passage through perihelion, these exotic explanations serve as reminders of how much we still don't understand about the universe beyond our solar system. Whether the comet emerges from conjunction as a thoroughly mundane, if unusual, object or continues displaying characteristics that challenge conventional explanations, it has already succeeded in expanding the boundaries of what we consider possible for visitors from other star systems. Beyond the scientific papers and technical debates, the story of 3I Atlas touches on something fundamentally human: our need to understand our place in the cosmos. This interstellar visitor represents more than just another data point. It's a catalyst that's reshaping how we think about everything from scientific collaboration to public engagement with discovery. The global response to 3I Atlas has demonstrated unprecedented levels of international cooperation in astronomy. From the moment of its discovery, observatories across continents began coordinating observation schedules, sharing data in real time, and harmonizing measurement protocols. This isn't just scientific business as usual. It's a prototype for how humanity might respond to future, potentially more significant astronomical discoveries. The coordination between space agencies for the Mars flyby observations represents a particular breakthrough. NASA, ESA, and other space organizations have developed new protocols for rapid response target of opportunity observations that will benefit future interstellar object studies. The lessons learned about data sharing, observation planning, and resource allocation are creating a new template for international space science cooperation. In classrooms around the world, 3I Atlas has become a living laboratory for science education. Students who might normally study static textbook examples are instead tracking a real-time scientific mystery unfolding before their eyes. The comet's accessibility through small telescopes and online data streams has democratized participation in cutting-edge astronomy. Teachers report unprecedented engagement when students realize they're looking at the same data professional astronomers are debating. The comet's combination of visual appeal and scientific mystery has proven particularly effective at inspiring interest in STEM fields among students who might not otherwise connect with traditional science curriculum. The 3I Atlas story highlights both the promise and perils of modern science communication. On one hand, the comet has generated genuine public excitement about fundamental science. Social media platforms have become hubs for sharing images, discussing theories, and following the latest developments. Amateur astronomers worldwide have contributed valuable observations that complement professional data collection. However, the story has also demonstrated how complex scientific concepts can become distorted in public discourse. The same characteristics that make 3I Atlas scientifically interesting, its unusual behavior, mysterious origins, and unpredictable nature, have also made it vulnerable to sensationalism and misinformation. Science communicators have faced the challenge of explaining the comet's genuine significance while addressing exaggerated claims about its potential meaning. This balancing act, maintaining scientific integrity while fostering public engagement, represents one of the central challenges of modern astronomy communication. The effort to study 3I Atlas is already driving technological innovation and creating economic opportunities. The need to track faint, fast-moving objects has accelerated development of new image processing algorithms and telescope control systems. Companies specializing in astronomical instrumentation have seen increased demand for sensitive detectors and rapid-slewing telescope mounts. The data management challenges posed by the flood of observations have stimulated advances in astronomical data infrastructure. New systems for storing, processing, and distributing large datasets are being developed that will benefit the entire field of astronomy long after 3I Atlas has departed our solar system. At a deeper level, 3I Atlas is prompting renewed discussion about humanity's place in the universe. The confirmation that objects from other star systems regularly pass through our neighborhood reinforces the concept that our solar system is not an isolated island but part of a dynamic, interconnected galactic community. Artists, writers, and philosophers have embraced the comet as a symbol and inspiration. Its journey from an unknown origin to a brief, brilliant appearance in our skies before continuing into the void resonates with fundamental human themes of mystery, transience, and exploration. The very name 3I Atlas reflects this cultural significance, combining the cold precision of astronomical designation with the mythological weight of a titan holding up the heavens. This blending of scientific and cultural narratives demonstrates how major astronomical discoveries continue to shape not just our understanding of the universe, but our understanding of ourselves. Perhaps the most important legacy of the 3I Atlas encounter may be how it prepares us for future interstellar visitors. The Vera C. Rubin Observatory, scheduled to begin operations soon, is expected to detect interstellar objects at a rate of several per year. The protocols developed, technologies refined, and public engagement strategies tested during the 3I Atlas campaign will provide invaluable preparation for this new era of interstellar astronomy. The comet has also strengthened the scientific case for dedicated interstellar object missions. Concepts that once seemed speculative now appear increasingly necessary if we're to properly study these visitors before they disappear back into interstellar space. The technical challenges encountered in trying to observe 3I Atlas with repurposed planetary orbiters have highlighted the need for spacecraft specifically designed for interstellar object reconnaissance. As we await 3I Atlas's reemergence from solar conjunction, we're left with the realization that this visitor has given us more than just scientific data. It has given us a glimpse of a universe more dynamic and interconnected than we previously imagined, a preview of coming discoveries that will fundamentally reshape our understanding of our cosmic neighborhood, and a reminder that the human drive to explore and understand remains one of our species' most defining characteristics. The cosmic clock is ticking toward a series of moments that will determine not only what 3I Atlas reveals about itself, but what it teaches us about the broader population of objects wandering between the stars. Each upcoming milestone represents a crucial test of our understanding, our observational capabilities, and our ability to extract meaningful science from phenomena that push every limit of current astronomical practice. The first critical juncture arrives on October 3rd, 3I Atlas's closest approach to Mars. At approximately 18.6 million miles, this encounter represents humanity's best opportunity to maintain surveillance of the interstellar visitor during the period when Earth-based telescopes begin losing sight of it. The mechanical eyes orbiting Mars will attempt observations never intended by their original mission designs, stretching technological capabilities to capture images and spectra of an object racing past at interstellar velocities. Success depends on variables beyond human control. If 3I Atlas maintains or enhances its current brightness levels, the Mars orbiters might capture detailed images of nuclear structure and coma dynamics invisible from Earth-based telescopes. However, if the comet fades from its September peak, even the most sensitive spacecraft instruments might detect only marginal signals, insufficient for meaningful scientific analysis. The data from this encounter will be precious but slow to arrive. Mars orbiters have limited communication windows with Earth, and the comet observations must compete with routine planetary science data for transmission priority. The first images might take days or even weeks to reach Earth, creating an agonizing wait for researchers who know this represents their last clear view of the comet for nearly a month. As mid-October arrives, 3I Atlas drops below 20 degrees of solar elongation, effectively ending routine observations from Earth's surface. The comet doesn't vanish suddenly but fades gradually into the solar glare, like a star at sunrise. Professional observatories with sophisticated coronagraphs and adaptive optics systems might snatch a few final glimpses, but for most practical purposes, the comet disappears from human view. This begins the most frustrating period for astronomers. Knowing the comet is experiencing increasing solar heating and potentially undergoing dramatic changes, yet being unable to observe them directly. The only information during this period will come from the limited perspective of Mars orbiters and any fortunate observations from spacecraft in other parts of the solar system. The moment of maximum drama occurs on October 29th to 30th, when 3I Atlas reaches perihelion at approximately 1.36 astronomical units from the Sun, hidden completely from Earth's view. The comet will experience solar radiation intensities unlike anything in its multimillion-year journey through interstellar space. This is when theoretical models predict the most dramatic transformations could occur. The nucleus temperature will soar, potentially activating volatile compounds that have remained stable throughout the comet's journey. The already extensive Coma might expand to even more mind-boggling dimensions. The mysterious anti-tail could intensify or transform into entirely new structures. Most significantly, the thermal and tidal stresses could cause the nucleus to fragment, an event that would fundamentally alter the comet's future evolution. The cosmic irony is profound. The moment of maximum scientific interest occurs precisely when human observational capabilities reach their minimum effectiveness. Whatever revelations occur at perihelion will remain largely hidden, preserved only in whatever indirect evidence survives for later analysis. During the first week of November, 3I Atlas reaches the midpoint of its conjunction period, when its angular separation from the Sun is smallest. This represents both the observational low point and potentially the activity peak for the comet. Solar heating reaches its maximum intensity, and if the comet survives intact, this is when its outgassing rates should be highest. For astronomers, this period becomes an exercise in theoretical modeling and speculation. Without direct observations, researchers must rely on computer simulations to predict the comet's behavior, knowing that any of these predictions could be completely overturned when observations resume. The most anticipated moment comes in the second half of November, when solar elongation increases sufficiently for Earth-based telescopes to relocate and track 3I Atlas. This will be a delicate operation. The comet will emerge in a different part of the sky, with uncertain brightness and possibly altered appearance. The first images could reveal anything from a dramatically transformed object to complete disintegration. Several scenarios are possible. The survivor, 3I Atlas, emerges largely intact but with enhanced activity, a larger coma, more developed tails, and continued unusual emissions. The fader, the comet appears significantly dimmer, having exhausted its most volatile materials during the unobserved perihelion passage. The multiple, the nucleus is fragmented into several pieces, each with its own coma and tail, creating a complex system to track and study. The ghost, only a diffuse cloud of dust remains, indicating complete disintegration during perihelion. The recovery observations will require careful coordination among observatories worldwide to quickly characterize the comet's new state and adjust observation plans accordingly. Assuming 3I Atlas survives its solar encounter, the post-perihelion period offers extended opportunities for study. Though the comet will be steadily fading as it moves away from the Sun, Earth-based telescopes will have clear views throughout this period, allowing for comprehensive monitoring of how an interstellar object behaves after its closest approach to a star. The viewing geometry will be particularly favorable for studying the comet's tail structures, which typically become most developed after perihelion. Different instruments will focus on specific aspects: spectroscopes monitoring chemical changes, polarimeters studying dust properties, and imagers tracking structural evolution. In March 2026, 3I Atlas will make a distant approach to Jupiter, though at much greater distance than the Mars encounter. While this won't provide the detailed views possible from Mars orbit, it may offer additional opportunities for observations by Jupiter-focused spacecraft, depending on their operational status and orbital positions. The scientific harvest from these critical moments will extend far beyond the immediate observations. Each measurement adds to our understanding of how objects from other star systems behave when they encounter ours. The specific questions researchers will be seeking to answer include: how does the composition of 3I Atlas compare to both solar system comets and theoretical models of exocometary formation? What physical processes can explain the persistent anti-tail phenomenon? How does the activity evolution of an interstellar object differ from that of solar system comets? What does the object's survival or fragmentation tell us about the internal structure of interstellar visitors? The answers to these questions will influence not just comet science, but our broader understanding of planetary system formation throughout the galaxy. Each interstellar visitor provides a unique sample from another stellar environment, and 3I Atlas, with its extreme characteristics, may prove to be the most informative sample yet collected. As we approach these defining moments, the entire astronomical community holds its collective breath. The coming weeks will reveal whether 3I Atlas is merely an unusually active comet or something that requires us to fundamentally rethink our understanding of small bodies throughout the cosmos. As we stand at this threshold of discovery, watching and waiting for 3I Atlas to reveal its secrets, we're participating in something much larger than the study of a single celestial object. We're witnessing the maturation of a new field of astronomy, the study of interstellar visitors, and confronting fundamental questions about our place in a galaxy filled with wandering worlds. This comet, in all its strange glory, represents more than just the third entry in a catalog of interstellar objects. It represents a challenge to our paradigms, an invitation to expand our thinking, and a reminder that the universe consistently produces wonders beyond our imagination. The story of 3I Atlas follows a pattern familiar throughout the history of science, but particularly pronounced in astronomy. Each time we develop instruments capable of seeing farther or measuring more precisely, we discover phenomena that don't fit our existing frameworks. When we built telescopes powerful enough to study comets in detail, we discovered they weren't the atmospheric phenomena ancient astronomers imagined, but cosmic wanderers from the solar system's frozen outskirts. When we developed the capability to detect objects from beyond our solar system, we found that each one, Oumuamua, Borisov, and now 3I Atlas, defies easy categorization and challenges our expectations. This pattern suggests that 3I Atlas, for all its strangeness, may be showing us something fundamental about the universe. That diversity is the rule rather than the exception, and that our solar system, while special to us, represents just one possible outcome of planetary formation processes. Regardless of what the coming weeks reveal, 3I Atlas has already secured its place in scientific history. It has demonstrated that interstellar objects can be far more active and complex than our first two examples suggested. It has pushed our observational capabilities to their limits and beyond, driving innovation in everything from telescope control systems to data analysis techniques. The comet has also demonstrated the power of global scientific collaboration. From its discovery by survey telescopes to observations by the world's premier observatories to the coordinated response of space agencies, the study of 3I Atlas has shown how modern astronomy operates as an international enterprise, transcending borders in the pursuit of understanding. The human dimension. But beyond the scientific papers and technical achievements, 3I Atlas touches something deeper in the human spirit. There's a profound sense of wonder that comes from realizing we're looking at an object that formed around another star, possibly billions of years ago, and has traveled through the vast emptiness of interstellar space to briefly grace our skies. This visitor reminds us that our solar system is not an isolated island, but part of a dynamic, interconnected galactic community. The same processes that formed the planets around our sun operated around other stars as well, producing their own families of worlds and their own populations of comets and asteroids. Some of these objects, like 3I Atlas, get ejected from their home systems and begin journeys across the galaxy, occasionally passing through other stellar systems like ours. As we await the comet's reemergence from solar conjunction, fundamental questions remain unanswered. Is 3I Atlas a typical interstellar object that happens to be the first we've seen with such advanced instrumentation? Or is it truly exceptional, representing a class of object unlike anything in our solar system? Does its unusual behavior reflect the conditions of its formation around another star? Or has it been transformed by its long journey through interstellar space, battered by cosmic rays and processed by unknown environmental factors? The answers to these questions will come slowly, pieced together from the observations collected during its brief passage through our neighborhood. Some mysteries may be solved in the coming months, while others might await future interstellar visitors or even spacecraft missions to such objects. The study of 3I Atlas represents just the beginning of a new era in astronomy. The Vera C. Rubin Observatory, scheduled to begin operations soon, is expected to detect interstellar objects regularly, perhaps several per year. Each new visitor will add another piece to the puzzle, helping us understand the diversity and prevalence of such objects throughout the galaxy. Future space missions, like the European Space Agency's Comet Interceptor, are being designed specifically to study such visitors. Where we currently must make do with repurposed planetary orbiters and hurried observation campaigns, future astronomers will have dedicated tools for interstellar object research. As we watch 3I Atlas complete its journey through our solar system and disappear back into the interstellar darkness, we're left with a renewed sense of cosmic perspective. We live in a galaxy where worlds and worldlets constantly exchange between star systems, where the raw materials of planet formation travel freely across light years, and where our own solar system regularly receives visitors from distant stellar nurseries. 3I Atlas, in all its green-glowing, anti-tail-sporting, brightness-defying strangeness, has given us a gift. It has shown us that the universe is even more wonderful, more diverse, and more mysterious than we imagined. It has reminded us that there are always new wonders to discover, new puzzles to solve, and new horizons to explore. The messenger from the stars will soon continue its journey, but the message it carries, that we live in a universe of infinite variety and endless discovery, will remain with us long after it has vanished from our view. We may never know all of 3I Atlas's secrets, but in trying to understand this mysterious visitor, we've learned something equally valuable: that the human drive to explore, to understand, to reach for the stars is itself one of the most powerful forces in the universe. And that, perhaps, is the most important message any messenger could bring.